We've looked at vapor power plants that operate on the basis of Rankine cycle. In this video, we're going to look at gas turbine power plants, and we will be looking at the ideal Brayton cycle. Now, gas power plants or gas turbine power plants, they tend to be lighter, they're more compact than the vapor power plants, so they're easier to transport as well, and that's why they are one of the kind of power plants that are easier to use for power generation. So with gas power plants, what usually happens is that the atmospheric air is drawn into the compressor over here, where it is compressed to a higher pressure, and then this air enters into the combustion chamber, mixes in with fuel, combustion takes place, and then the combustion products are expanded through the turbine, and they are then discharged to the surroundings after extracting a net amount of work. What you see from this figure is that the turbine and the compressor are connected by the same shaft. So some part of the turbine work that is developed is used to drive the compressor, and all of the rest of it is used for electricity generation. Now, gas turbine power plants can operate on either the open or the closed basis. By open, what we mean is this schematic that is being shown here, where we draw in the atmospheric air and use that in the compressor, and then mix it in with the fuel in the combustion chamber. Whereas with the closed form of the gas power plant, we would have, for example, let's say the working fluid receiving an energy input by heat transfer from an external source. That external source could be a gas-cooled nuclear reactor, and then the gas that would be exiting the turbine would be passed through another heat exchanger where it would be cooled before it enters the compressor again. So this is the open basis, and then we've got the closed one as well. And why is it called open? Because it is open to the atmosphere, or open to the atmospheric air. This would be the closed basis, where we've got, like I said, we've got this cycle that is being completed by the addition of another heat exchanger in there. And now we have to basically idealize the gas power plant as well. So when we're looking at a gas power plant, essentially we're talking about a Brayton cycle. And right now we're going to be looking at the air standard Brayton cycle, the ideal air standard Brayton cycle. And in this kind of cycle, we're idealizing it. So there's going to be two major idealizations that we're looking at in the air standard analysis. The first is that the working fluid, which is air, we assume that it behaves as an ideal gas. And the second is that the temperature rise that would happen here because of combustion, we, instead of looking at the combustion products and the reactions, we just go ahead and identify it by a heat transfer taking place through an external source, so heat content being added into the heat exchanger instead of looking at the combustion chamber and its products. And then one important thing that we need to remember is that we need to use the air data table from table A22 in Shapiro's book of Thermodynamics to work with the air standard analysis, because we need to find out the enthalpies at each state. So looking at this schematic here, I have to first of all identify the states, and because air enters into the compressor here, so I'm going to identify this as state 1, and then at the exit of the compressor I'm going to have state 2. At the inlet of the turbine I'm going to have state 3, and the exit of the turbine I label as state 4. So now I can go ahead and basically find out the work done or the heat contents added or removed in this entire cycle as well. So the work done across the turbine, for example, I could write that. So work done across the turbine, and essentially we're looking at the work that is developed per unit mass. That is going to be equal to, and right now I'm looking at state 3 and 4. I can identify it by using the arrow directions here. With turbine I've got work done taking place, so the direction is going to be outwards here. With the compressor, I've got work that is being added into the compressor here. So let me just label these here. And I've got work done across the turbine here. And Q dot in and Q dot out are already labeled. So when I've got the situation where the arrows are pointing outwards, I'm going to have enthalpies in terms of the enthalpy at the inlet minus the enthalpy at the outlet. So because the arrow is pointing outwards here, so work done across the turbine, that's going to be equal to H3 minus H4. And then I've got work done across the compressor that I can look at. And now because the arrow is pointed inwards, so instead of looking at the initial minus final state, I'm going to have it flipped, final minus initial. So it's going to be H2 minus H1. That's a good little trick to have up your sleeve if you want to analyze any kind of cycle really quickly. Then you've got the work done in, the heat content that is being added into the system. And again, because the arrow is pointed inwards, so I'm going to have it as the final state minus the enthalpy at the final state minus the enthalpy at the initial state. So it's going to be H3 minus H2. And last of all, I've got Q dot out that I need to account for. And again, with the arrow pointed outwards, I'm going to have initial minus final enthalpies. That's going to be H4 minus H1. So now that I've written all of these, I can go ahead and write down the total work done across the cycle, or the net work out, which is going to be work done across the turbine minus work done across the compressor. And using that, I can also go ahead and write the efficiency, or the thermal efficiency, for the cycle, which is going to be equal to the net work out divided by the heat content that is added into the system. And using this, I can just plug in these three in terms of their enthalpies to find out the thermal efficiency. So the enthalpy form of the thermal efficiency is given as it is here, and one other important equation or variable, which is known as the back work ratio, needs to be defined as well, just as it was for the vapor power plant. So the back work ratio is a ratio of the work that is basically provided within the cycle, so work done across the compressor divided by the work that is extracted through the cycle. So that would be work done across the turbine. So it's given in this form, divided by work done across the turbine. And then the values can be substituted here in terms of enthalpies. Now what the back work ratio here indicates is how much of the work that is developed by the turbine is required to drive the compressor. When we talk about gas turbines, the value for the back work ratio ranges from 40 to 80%. And if you compare that to the vapor power plants, for vapor power plants, the back work ratio is only about 1 or 2%. So by comparison, you can see how much a relatively larger portion of the work developed by the gas turbine is required to drive the compressor, provided that we are looking at the same level of pressure rise. Now we can go ahead and look at the PV diagram and the TS diagram for the ideal Brayton cycle, or the air standard ideal Brayton cycle. So let's just look at process 1 to 2 first of all. Obviously, it is happening across the compressor, so that means that compression is taking place. And because we're looking at an ideal scenario, so that means that this compression should be taking place in a way that is reversible. And for it to be reversible, that would have to be an isentropic process, because an isentropic process is reversible and adiabatic as well. So 1 to 2, you're going to have state 1 here, because it's compression, so it's going to move vertically upwards on the TS diagram until it arrives at state 2, which is at a higher pressure. So you got 1 to 2, which is an isentropic compression process. And on the PV diagram, this translates into meaning that, first of all, 1 to 2 has to be on the constant entropy line. And the second, because it's compression, so the specific volume has to be decreasing. So the constant entropy line is of this form on the PV diagram. So we're going to have 1 to 2 process that is taking place here, where this line is a constant entropy line. And now from 2 to 3, because heat addition is taking place, and that heat addition is going to be taking place at a constant pressure. So 2 to 3 is going to be on the constant pressure line on the TS diagram. So we're going to have the constant pressure line, which looks like this on the TS diagram, where we've got this as the constant pressure line. And 2 to 3, for it to be a constant pressure line, it has to be a horizontal line here. So we've got 2 to 3 here. We should indicate the direction of the processes not just by the state numbers, but by arrows as well. So you've got 1 to 2 here, and 2 to 3 over here as well. And now from 3 to 4, it's happening across the turbine. So what happens across the turbine? Expansion takes place. And this expansion, for it to be ideal, has to be isentropic as well. So for it to be isentropic, it has to be a vertical line on the TS diagram. And that's going to look like, that's going to look something like this on the TS diagram. So this is process 3 to 4 on the TS diagram, and 3 to 4 on the PV diagram is going to be on the constant entropy line. And because expansion is taking place, so the specific volume has to be increasing. So let me just indicate this as the horizontal line. So 3 to 4 should be coming down, let's say, onto this line somewhere here. So this is our process 3 to 4 on the PV diagram. And now to close the loop, it's going to be from 4 to 1. We could just close the loop as we have started it. So we go back from 4 to 1. Or we can think about it as well, because heat rejection is taking place now, and it's going to be taking place at a constant pressure. So we're going to go from 4 to 1 on this constant pressure line to arrive back at state 1. And over here, again, the constant pressure line is going to be the horizontal line. So this is horizontal. And yeah, so this is how the ideal Brayton cycle looks like on the PV and the TS diagram. Important point to note here, I was asked this question a while ago, that why do we not have, or why do we not prefer for this 3 to 4 line to not be a vertical line and instead be, of this form, let's say. The reason for that is, if I had not explained it properly, is that for an ideal cycle, we want all the processes in that cycle to be reversible. When we move on this line, if let's say this was 3 to 4 dash, for example, when we're moving from 3 to 4 dash, the entropy has increased now for that process. And now we cannot decrease this entropy in a way such that the process is reversible, such that the process does not have any effect on the system and the surroundings as well. So instead, we need to go for a process in which entropy doesn't change, so we can go back onto it and make this process reversible as well. That's the reason why we have this as the isentropic process here for the ideal Brayton cycle. Another thing that I already talked about is that we are looking at the ideal air standard Brayton cycle, and we made the assumption for this that we would be using the air data table, table A22 from Shapiro's book. And for that, because of that assumption, we use something of a ratio of pressures. So, for example, if I'm looking at the pressure ratio of P2 by P1, that can be equated to the relative pressure ratio of PR2 by PR1, and PR2 and PR1 are going to be given to you in the air data table, where what PR means is relative pressure. It's not actually a pressure, it is a function of temperature, it is a function of the gas constant as well, it's a function of entropy as well, but the entropy remains constant, and the gas constant remains constant as well. So the relative pressure is actually a function of temperature, and the value for it is given in your air data table. So if, for example, you have this pressure ratio given to you, you can find out one or the other, PR1 or PR2, and subsequently go ahead and find out the enthalpies at all the states. And then if you look at the pressure ratio of process 3 to 4, so over here, you're going to have P3 by P4 or P4 by P3 equals PR4 by PR3. And then you can use the relation P4 by P3 equals P1 by P2. And why are you using this relation? Because the air is flowing through the heat exchangers of the ideal cycle at constant pressure. So then you can equate the pressure ratio. So P4 by P3 is equal to P1 by P2. And using this, you could substitute that in the other pressure ratio, which is this one here. So you can substitute P4 by P3 equals P1 by P2 if you do not have P4 by P3 given to you in any case, in any question. Now we just look at another scenario when we make another assumption, and this previously we had looked at the ideal air standard Brayton cycle, and now we're looking at the ideal cold air standard Brayton cycle. And the difference between these two is that the other idealizations remain the same for the ideal cold air standard Brayton cycle as well, but we add one more idealization to it where we assume that the specific heats are constant, and then we sacrifice some of the accuracy, but now using these idealizations, instead of looking at, for example, enthalpies are going into air data tables, we can just go ahead and look at temperatures, and using those temperatures we can just find out let's say the work done or the heat contents or the thermal efficiency. So now, because we've assumed that the specific heats are constant, then enthalpies can be written in terms of delta H, because delta H is equal to Cp into delta T. So I could just write this in terms of Cp for the air, which is being treated as an ideal gas, multiplied by T3 minus T4, right? So I don't even need to go ahead and look at the data tables anymore if I have all the temperatures, for example, given to me. And just like that, I'm going to have this work done across the compressor, which was equal to H2 minus H1 equal to Cp into T2 minus T1. And I could go on and keep doing this for the heat content added, the heat content removed, And then even in terms of thermal efficiency, now I could write it in terms of the temperatures because Cp would cancel out. I wouldn't need to account for that, but I would need to account for Cp when I'm looking at the work done across the turbine, for example. But when it comes to thermal efficiency, I Cp is going to get canceled out basically. So it's going to be your efficiency, thermal efficiency, which is going to be in terms of temperatures, and it's going to be 1 minus T4 minus T1 by T1 minus T2. And just like that, you could also go ahead and write the back work ratio as well. In a lot of cases, though, that it's entirely possible that uh, you've got temperatures that are not given to you in a lot of cases. And instead, you've got pressures given to you. So then you need to convert from pressures into temperatures. Also, so for example, if I'm looking at to convert it into the pressures into temperatures, then I could go ahead and use the relation for polytropic processes, which is PV to the power n, which is equal to constant. And for this kind of idealization, I'm going to have T2 by T1 equals P2 by P1 to the power. You could write it K minus 1 by K, or you could write it gamma minus 1 by gamma, where you've got gamma or K, which is the specific heat ratio for air. This ratio is equal to 1.4. So you could use these two equations if you don't have temperatures given to you to find out the temperatures, and then going ahead and doing the entire process to find out the work done, the heat contents, the thermal efficiency, the back work ratio.